In section 2.2, we're going to look at some more graphs and displays of data. So it's kind of a continuation of section 2.1. The first thing we're going to look at is a stem and leaf plot. And when you construct this, you will have a vertical line, and then you will have a horizontal. And what you're going to do is you're going to put the first one or two digits of the number on the left, and then you're going to put, and those will be your stems, and then you're going to put your leaves on the right. And each leaf, if you'll look in the definition, has to be a single digit. So that will be your ones digit will always be a leaf. So what you do is you need to locate the smallest number in the data set. This is the number of text messages sent by 50 cell phone users, and the smallest one we see is 16. So we would have a 1, and that would be our stem, and then we would have a 6, and that would be our leaf. And then if you look back up, there's another 1 number, and that's 19. So we skip over a little bit and put our 9. You want to skip over enough to tell that the 6 and 9 aren't together. And then we move on to the numbers that are in the 20s. So we look and we find a 20. So that would be 2, 0. And then there's a 23. So that would be a 3. And then you just continue on, and you have to go in order because these leaves should be in order from least to greatest. So you want to make sure you go in order and don't skip any. So as we finish this out, there was a 24, a 26, another 26, a 28, and then 4 29s. And then you move on down to the 30s, and there were 2 30s. 32, and there are 4 33s, and then a 34, a 38, and a 39. And then we move on to the 4s. And you just continue going through your data and putting in the numbers like I'm doing here. And when you get finished, hope I've left enough room, I'll have to squeeze these in at the bottom. When you get finished, you'll notice that there may be a stem or more than one stem that doesn't have any leaves on it, and that's okay. You still have to include whatever you start with, you have to count in order, so don't skip any numbers, even though there may not be a stem with using that number. So now we're getting down here, and there's a 99, a 102, a 115, a 122, and there's not a 130 number. So that one will be left blank, and then there's a 149. And then very important, you need to make what we call a key, and the key tells us what these numbers represent. So if you're looking at it, what does it mean when you see a 4 with a 0 over here or a 10 with a 2? So you just pick any one of them. It doesn't matter. I'm going to use the 10, 2. And you say that the 10 on the left with the 2 on the right is the same thing as 102, and that's the key. The nice thing about these is you can tell just by looking at it where the majority of the data lies. So you can tell almost all the data actually lies between 20 and in the 20s and 80s. So if I went from the 20s to the 80s, that's almost all the data points. Or you can say, well, I can look here and see that over half of the data lies here, but in the 20s and 50s. So you can look and see real easily where the majority of your data lies. On example 2, we're going to use the same set of data, but it says that instead of using one stem for each one, that we're going to have 2 rows for each stem. So instead of having 1 row with the 1s and 1 row with the 2s, we're going to have 2 1s, 2 2s, 2 3s, and so forth. And I'm not going to reconstruct the whole thing here. I'm just going to do a few rows to give you an idea what it's talking about. So here we would have 2 rows of 1, 2 rows of 2, 2 rows of 3. And the way you put these in is if it falls from 0 to 4, it would go on the first row, and if it falls from 5 to 9, it would go on the second row. So on this one, we don't have anything until 6, so the first row would be blank with the 1s, and we would have the 6 and the 9. On the 2s, you would have the 20, so the 0, the 3, and the 4 on the first row, and then you would have the 6, 6, 8, 9, 9, 9, 9 on the second row. So that's, so you can see here what it does. It keeps the rows from being as long, and you could do that all the way down. So it's the same thing. It's just specifying that you want 2 rows for each of the stems. And then again, once you conclude, finish with this one, it again will let you see kind of where most of the data points lie. You can really look at the graph easily and see where most of the numbers are. Okay, the next one, and we're not going to construct this. I put the picture in here with it so we could just talk about it. This is called a dot plot, and all you're doing is you're going to have a number line, and the number line needs to have from the smallest, in this case, we're doing this text messages again, the smallest number of text messages, and then be able to go all the way up to the greatest. So the one that they constructed was counting by 5s and started at 15. And you'll notice these aren't real exact because they didn't count by 1s here. It's 15, 20, 25, 30. So you kind of have to estimate where the points will lie. So there would be our 16 right here, and then our 19, and then our 20. And then you'll notice when there are multiple points, so we had 2 26s. So there's 2 points here where the 26s are. And then you can see here where the 29s are, there's 4 points, and so on. And that's how you create a dot plot. And again, this one makes it pretty easy to identify where most of the entries are. So you can see real quickly here that most of the entries are between, and I pointed this out on the stem and leaf, most of the entries are right here from the 20s to the 80s. So between 20 and 80 would be most of your points. And then you can see here, if you look at this, you've got, if you kind of draw a line here at 100, there's only 4 that were more than 100. So again, this is an easy way to look and see where your data points lie. Okay, the next kind of graph we'll look at is a pie chart, and this is a very common one. You'll see these a lot in, if somebody's making a presentation and they want to show the data, it's very common to see pie charts. And a pie chart is called a pie chart because it's circular, and you have pieces cut out of it, and those pieces are called sectors. So you'll see that a pie chart is a circle divided into sectors that represent the different categories, and the area of each sector is proportional to the frequency. So how often it occurred, that determines how big your piece of pizza is or your piece of pie is. So on this one, you have to do a couple of things. First thing you want to do is you always want to figure out the total number. So here we have the number of earned degrees in 2014, and we have associates, bachelor's, master's, and doctoral. And if you add all of these up, that would be your total. And it's very important that you find your total on these. So if you add those up, you get 3,805. And what you're going to be doing, you'll notice I left the pie chart here so it would look neat instead of trying to draw a circle and create this. You'll notice that these are all percentages. So what you're going to need to do is you're going to need to find percentages. And remember that a percentage is a part out of the whole. So what part are associates out of the whole? So for the first one, we'll do the number out of the total, and that was 1,003 out of 3,805. And you'll just do this on your calculator. You'll divide those, and you're going to get about 0.264. And remember to change to percent. We learned earlier that you move the decimal 2 places to the right, because what we're doing is we're actually multiplying by 100, and that's where the 26.4% comes from. So you'll see here they did 26.4%. But what we're going to do with this is we need to figure out how big that sector needs to be. So if we think in terms of this as being the whole circle is 360 degrees, this is the part of 360. So what you're going to do after you get this decimal is you're always going to multiply by 360, and that's going to give you how many degrees the sector needs to be within that circle. So when I multiply that, I get 95 degrees. Now keep in mind that a 90-degree angle is a right angle. So you'll notice here that this is slightly bigger If you're looking at this angle right here, that's slightly bigger than 90 degrees, or slightly bigger than a right angle. And then we'll do the same thing with the others. So we'll go 1870 over 3805, and that gives me 0.491, which is 49.1%. You'll see that right here. So we know that's almost 50%. So this should be almost half the circle. So when we multiply that by the 360 degrees, we get 177 degrees. And half the circle would be 180. So you can tell this is almost half of the circle. And that creates the bachelor's degree area. And then we would do the same for the last two. So we get 754 over 3805. And then that's 0.198 multiplied by 360. And again, there you see the 19.8%. And we multiply by 360 and get 71 degrees. So you can see that angle there. And then the last one is the 178 over 3805. And that comes out to 0.047 multiplied by 360 is just 17 degrees. And you can tell here this one's a very small. And they'll typically label inside if there's room for it, but if it's a really small sector, then they'll put it outside. And that's how you create a pie chart. And again, most of these, you're going to be doing all of your homework online. So you may have to find the decimals, the percentages, and the degree, but you're going to be matching it to a picture that they already have drawn. So you're not going to have to draw the circle yourself. Okay, the next one we're looking at is called a Pareto chart, and this is a vertical bar graph, and the bars represent frequency or relative frequency, just like the histogram. But what you're going to notice here is the bars don't touch each other, and the way they position it is so that the highest frequency occurs first, and you can tell here looking at this, and then the bars get shorter. So you always do it to where it's in decreasing height. And this one was accidents, leading causes of death in the United States. The accidents, cancer, respiratory disease, heart disease, and stroke. So the largest one of these was the heart disease, which was 614,000. So you can see here, and they counted by, these are in thousands, so 70,000, 140,000, 210,000, and so forth. So when you get up here, this would be 630,000 at the top. So that's just a little bit below that for the 614. And then the next one was real close to that, was 591. So again, they went down a little bit. And then these next three were down lower. So you can see with the Pareto chart that it just goes down from the greatest to the least. Next, we have graphing paired data sets. If you've had very many algebra classes in high school, then you'll probably remember having to do scatter plots or to plot X's and Y's. And that's what a graphing paired data set is. You're pairing two things and then graphing. So it's like a scatter plot. So when each entry in one data set corresponds to an entry in the second data set, these are called paired data sets. And in a scatter plot, the ordered pairs are graphed, but you'll notice that they're not connected. But you'll be able to tell a relationship between the two variables based on the graph when you get finished. And then the last one's called a time series, and that's just showing a data set where you're looking at the entries taken at regular intervals over a period of time. So your horizontal axis will always be time. So again, I left these graphs on here rather than constructing them because they have a whole lot of points. And this one here is showing Fisher's iris data set, and you can read the description. But what it's talking about is the petal length and the petal width in an iris. And you can see here that you've got a whole bunch of little points down here showing you that when the petal length is 10, then the petal width looks like it's about probably 2.5 or 3 if you're looking at this very first point. And then you've got a bunch of points here. And then we jump up here and you have a whole bunch more points up here. So you can say when the petal width is 40, then, or petal length is 40, then the petal width is 10. And that's what each one of these points represents. That this is how long the petal is, and then if you go over here, this is how wide it is. So there would be one with a 50 millimeter length and a 10 millimeter width, and that's creating a scatter plot. And they ask you to, as petal length increases, what tends to happen to petal width? So they're asking you to interpret that. And this is real simple. It looks like as the length gets longer, it looks like the width gets wider. So you could say, just create a sentence here. As petal length increases, petal width also tends to increase. And you'll always have some points in a scatter plot that don't seem to follow the other pattern, but in general, you can see that this is going up like this. So as you're moving to the right, the points are moving up. And we'll talk more about scatter plots when we're looking in chapter 9. All right, and then the last one we're going to look at is the time series chart. And a time series chart will always use time, and it may be minutes, hours, months, days. In this case, we're looking at years. But going across the graph, this will always be time, and that's why it's called a time series chart. And what we're looking at is the number of motor vehicle thefts and burglaries in the United States for the year 2005 through 2015. So in 2005, it looks like we have 1.24 vehicle thefts. And so you'll come up here and you'll see that this is at 1.2, just a little bit above 1.2. And then in 2006, 1.2, so it's right there on the line. And in 2007, 1.1. So it's moving down. And then these will be connected when you do these, because each one of them is a single point. So they go across and you connect them. And that's what a time series chart looks like. And then it asks us to describe any trends. And you'll notice this one was the number of vehicle thefts. You could, if you wanted to practice, you could do the burglaries on this same graph. Just go in and plot where the burglaries are and see what it looks like. So the trend it looks like here is, over time, it looks like the number of thefts is going down. So we could say that the number of thefts decreased, and you can see this, it continues to decrease until about 2011, and then after that it seems like it's just kind of staying, even you could even say about 2010, but it's kind of decreasing and then it just kind of levels off. So the number of thefts decreased until about 2010 or 11, I'm going to say 2011, then remain the same.